Hello learners, in this lecture we will see how the testing of aggregates has to be done. So before understanding the testing of aggregates, we need to understand one particular term, and after that we'll try to see how it has to be understood. So now let us say these are the aggregates what we already seen, right? So it is clear for me that this is a fine aggregate and this is a coarse aggregate. Now if I ask you to tell me the size of this fine aggregate and also the size of this coarse aggregate, uh, will you be in a position to answer this? No, right? It's quite difficult for us to understand or to tell what is the exact size of the coarse aggregate or what is the exact size of the fine aggregate that is present here. So in order to tell that, or in order to understand that, we need to understand one small term which is called as fineness modulus. So first we'll try to see what is fineness modulus, then we'll try to see what is a practical application of that, and once we have understood that, then we'll be in a position to tell what is the size of the particle that we have in this particular coarse aggregate and in this particular fine aggregate. Yeah. So fineness modulus is defined as the sum of a cumulative percentage written on the sieve, and you have to divide it by 100, right? Next, the fineness modulus is a numerical index number which gives us some idea of the coarseness and fineness of the aggregate. That means it's going to give us one particular number, okay? And based on that number, I'll be in a position to tell whether the aggregate what I'm using, whether it is a coarse aggregate or whether it is a fine aggregate, right? The next point is very important. Fineness modulus gives us an idea of the mean size of the particles present in the entire body of the aggregate. That means, suppose if I ask you tell me the size of this aggregate what we have, then you cannot directly tell me, let us say we have only 20 aggregate present in that, so we can never tell that. So instead of that, I can tell you the average particle size. That means, let us say the particle size in this coarse aggregate is somewhere in between 10 to 20 so it's going to give us the average size of the particle, and this average size is understood with the help of a fineness modulus. So to put it in a better way, so fineness modulus, it is a number which indicates the average size of the aggregate, right? So it's going to tell us the average size. Let us say if I want to find the size of this, then let us say the average size of this is in between 1.18 to 2.36. In this way, I can try to tell that. So this understanding will come only when you know the fineness modulus, and how that fineness modulus has to be understood, that we'll try to see in the next slide, how it has to be done practically. Yeah. So this is how we try to do. So for that we require the sieve number. So these are the sieve what I have, that is a 80 sieve. Then we require a 40 sieve. Then we require a 20 sieve. We require a 10 sieve, 4.75, 2.36, 1.18. Then we require a 600 micron, 300 micron and 150 micron. So how these sieves are going to look, that we'll try to see. First we'll see the sieve size of 80, 40, 20, 10 and 4.75. These are usually for the coarse aggregate, and if you're going for the fine aggregate, we know that fine aggregates are those aggregates whose particle size is less than 4.75 So for that we have to use 2.36, 1.18, 600, 300 and 150 micron. So see, if you're going for the coarse aggregate, then this is the sieve size what we have. Let us say this is a 80 sieve, then we have a 40 sieve, then we have a 20 sieve, then we have a 10 sieve, then we have 4.75 sieve. So in this way the sieves are kept ready. You can see it here as well. So these are the different Indian standard sieves what we have, 80, 40 and so on, right? Similarly, if you go for the fine aggregate, in that case these are the sieves what we have. Let us say this is 2.36, then we have 1.18, then we have 600 micron, 300 micron and 150 micron. So whatever is given, based on that we are going to do the test. But in this test we'll try to do it common, that is for coarse aggregate and fine aggregate we'll try to do one simple thing that is called as fineness modulus, and we'll try to see the practical application of that. But practically when you do it on the side, then if you have a fine aggregate, then you have to follow this particular steps what I'm going to explain in the next lecture. And this is the sieve sizes that you need to use, that is 4.75, 2.36 and all. And if you want to do the test for the coarse aggregate, okay, in that case this is the size of the sieve that you require, and based on that the procedure will be followed. But now we'll try to see for the we'll try to see the meaning of fineness modulus, right? So I hope the basic understanding is clear up to here. Yeah. So how to do that? First you have to take 100 gram of the aggregate. Let us say you've taken some, yeah, 100 gram of aggregate has to be taken first, and this is the sieve size that you need to arrange. You'll be arranging a 80 here, and after 80 you're going to arrange the 40 sieve below that. Then you're going to arrange the 20 sieve. Okay, then you're going to arrange 10 sieve, and in this way you have to try to do that. Yeah. So once you arrange that, you have to try to shake this with the help of sieve shaking machine, or manually with the help of hand. You can try to shake it. So as a result of what will, as a result of that, what is going to happen? The aggregates which are smaller in size, they try to settle down, and which are bigger in size, they try to remain in the same position, right? Let us say this is my 40 mm size of the sieve, and if the aggregate size is, let us say, 20 mm, then it's going to pass through this sieve, and it will be retained on this. And even if it is smaller than this is 20 mm, even if it is smaller than 20 mm, let us say 10 mm, then it's going to pass through this, and it's going to settle here, right? So this is how that is, this is how those things are going to happen. And finally, once you're done all those things, what you need to do, you need to individually weigh what is the weight that is retained on this. Let us say 40 mm, on 40 mm certain aggregates will be remaining. Even on the 20 mm sieve, certain amount of aggregate will be remaining. On the 10 mm sieve, certain amount of aggregate is going to remain. You have to take it out, and you have to individually weigh them. So this is how the procedure is going to go. So we'll try to see that. So let us say on 80 mm nothing is retained, so I've written it here 0. On 40 mm sieve, let us say 25 grams of the aggregate is retained, so I've written it here 25. On 20 mm, let us say 75 grams of the aggregates is retained, I've written 75 here. On 10 mm, on 10 mm sieve, 100 grams of aggregate is retained, so written 100. So in this way, whatever aggregates is retained, you have to measure it with the help of a weighing machine, and based on that, you have to write it here. So once this is done, next you have to write the percentage retained. So how this percentage retained is going to be done? It's very simple. Let me do it here. For that, you have to take this. Let us consider for this 75. So 75 is the weight retained on the sieve, divide by how much amount of aggregate you have taken initially, 1000. So divide it by 1000, and since I want it in terms of percentage, I'll try to multiply this by 100. So these two zeros are gone, these two zeros are gone. 75 divided by 10 comes out to be 75, 7.5 percentage. So that is why I written 7.5. Similarly, do it for 100, 300, 200, and so on. And these are the percentage what is retained. So once the percentage retained is done, the next task is very simple. Coming to the cumulative percentage weight retained. That means you have to add all these things. So this 0 you have to write it here. Then 0 plus 2.5 will be 2.5. 2.5 plus 7.5 will be 10 for me. 10 plus 10 will be 20. 20 plus 30 will be 50. 50 plus 20 will be 70. 70 plus 10 will is going to be 80. 80 plus 7.5 is going to be 87.5. 87.5 plus 7.5 is going to be 95, and 95 plus 5 is going to be finally 100, right? So once these things are done, try to add everything, and if you try to add everything, what you're going to get? You're going to get 515. You can try to verify the answers what I've written it here. Try to do it manually if you want, and you're going to get 515. And from here, the real play is going to happen. So finally, what I require, I need to find the fineness modulus, and to find the fineness modulus, the formula what we have is total cumulative percentage weight retained divided by 100. What is my total cumulative percentage weight retained? This is cumulative. The total means you have to add everything. Finally, I've got 515. So let me add it. That is 515. And if I divide that 515 divided by 100 is the formula for that, I'm going to get 5.15. So by the definition, we told you that fineness modulus is a numerical number, and this is that numerical number which is called as 5.15. So what we are going to do with this, now this number will tell us what is the size of the particle, and how it has to be understood, we'll try to see that. I'll quickly write them one by one here. So let us say, okay, yeah, yeah. So let me start from here. Let us say this is number 1, this is number 2, this 600 micron is number 3, 1.14 is number 4, this is number 5, this is number 6, number 7, number 8, number 9, and let us say this is number 10. This is how the procedure is. You have to start numbering it from the bottom. That is why I started to number it from the bottom. What is my answer? My answer is 5.15. That means this 5.15, is it lying in between 5 to 6? Do you agree with me? 5.5 is lying in between 5 to 6. Now try to see 5 and 6 number. So 5 and 6 number, where it is? So this is 5 and this is 6. That means it is lying in between this. It is lying in between this, right? 5 and 6, 5.51, 5.15 is lying somewhere here. That means it is lying in between 2.36 and 4.75. So I'll write it here, 2.36, 2.36 and 4.75. right? So now we got the answer. That means I'll go back to put it in a better way. That means whatever aggregate we had seen no initially, that means if I ask you what is the size of the aggregate here, then I've told you the fineness modulus. So with this fineness modulus, I've come to a conclusion that whatever aggregate is present in this particular sand, it lies in between 2.36 to 4.75. So this is the practical importance of the fineness modulus. So fineness modulus is going to give you the average size, and this is my average size, that is I'm telling, right? It lies in between 2.36 to 4.75. So with this number we are going to get the fineness modulus of the sand. So this is the practical importance of the fineness modulus, and now we'll try to see how it has to be understood in a more better way. So coming to the conclusion part, we got answer as 5.15. That means it is lying in between 4.75 and 2.36. I already explained, right? So this means the average size of the aggregate lies in between 2.36 and 4.75 mm. So if fineness modulus is more, that means the aggregates are coarser, and if it is less, then the aggregates are finest. So the very important point is that if fineness modulus increases, then the coarseness is going to increase. If fineness modulus is going to increase, the fineness is not going to increase, the coarseness is going to increase. So what do you mean by this? That is, now you have to concentrate here. So that is, we got the fineness modulus in between 2.36, right? We got it as 5.15, and 5.15 lies in between 2.36 to 4.75. Let us say I got a fineness modulus of 8.15. So this 8.15 is going to lie in between this 40 and 20, right? So that means if the fineness modulus is increasing, then what is happening? Your aggregate size are increasing from 20 to 40. So as a result of that, what is happening? The coarseness has increased. So always whenever the fineness modulus increases, it means the coarseness of that particular aggregate is going to increase, right? And if the fineness modulus is more, then what is going to happen? Surely your aggregates are going to fall in the coarse aggregate category. So with this understanding, again we'll try to see the other 3 points. Yeah. So the finest modulus of a coarse aggregate, usually it lies in between 6 to 7, and for the fine aggregate, the finest modulus lies in between 2 to 3. So always remember, the finest modulus for the coarse aggregate is greater in comparison to the fine aggregate, and it lies in between 6 to 7 for the coarse aggregate, and for fine aggregate is going to lie in between 2 to 3. So the sand having a finest modulus of greater than 3.2, usually we don't use it for concreting, right? So again, based on the finest modulus, the sand what we have, that is a fine aggregate what we have, it is classified in three ways. One is a coarser sand, the second is called as medium sand, and the third one is called as fine sand. If your finest modulus is in between 2.2 to 2.6, then we classify that as a fine sand. If my finest modulus is in between 2.6 to 2.9, I consider that to be a medium sand. And if my finest modulus is in between 2.9 to 3.2, I consider this to be a coarse sand. So what is the practical application of this? The practical application of this is when we do the mixed design, that is in the chapter 3, we are going to check all these things, what is the finest models, and based on that we are going to do the calculation, and based on that our mixed design will be prepared. So these are the use of finest modulus, and with the help of this the mixed designs is going to be carried out later. Yeah, so in the next lecture we'll try to see how this test has to be done practically in the lab, and we'll try to understand them separately for fine aggregate as well as for the coarse aggregate. I hope these things are clear. We'll see you back in the next lecture. Thank you.